quantum computer?
A quantum computer is a computation device that makes direct use of quantum mechanical phenomena, such as superposition and entanglement, to perform operations on data. Quantum computers are different from digital computers based on transistors. Whereas digital computers require data to be encoded into binary digits, each of which is always in one of two definite states, quantum computation uses qubits, which can be in superpositions of states. A theoretical model is the quantum Turing machine, also known as the universal quantum computer. Quantum computers share theoretical similarities with non-deterministic and probabilistic computers. One example is the ability to be in more than one state simultaneously. The field of quantum computing was first introduced by Yuri Manin in 1980 and Richard Feynman in 1982. A quantum computer with spins as quantum bits was also formulated for use as a quantum spacetime in 1969. As of 2014, quantum computing is still in its infancy, but experiments have been carried out in which quantum computational operations were executed on a very small number of qubits. Both practical and theoretical research continues, and many national governments and military funding agencies support quantum computing research to develop quantum computers for both civilian and national security purposes, such as cryptanalysis. Large-scale quantum computers will be able to solve certain problems much more quickly than any classical computer using the best currently known algorithms, like integer factorization using Shor's algorithm or the simulation of quantum many-body systems. There exist quantum algorithms, such as Simon's algorithm, which run faster than any possible probabilistic classical algorithm. Given sufficient computational resources, however, a classical computer could be made to simulate any quantum algorithm. Quantum computation does not violate the Church-Turing thesis.
Basis.
A classical computer has a memory made up of bits, where each bit represents either a 1 or a 0. A quantum computer maintains a sequence of qubits. A single qubit can represent a 1, a 0, or any quantum superposition of these two qubit states. Moreover, a pair of qubits can be in any quantum superposition of 4 states, and 3 qubits in any superposition of 8. In general, a quantum computer with qubits can be in an arbitrary superposition of up to different states simultaneously. This compares to a normal computer that can only be in one of these states at any one time. A quantum computer operates by setting the qubits in a controlled initial state that represents the problem at hand and by manipulating those qubits with a fixed sequence of quantum logic gates. The sequence of gates to be applied is called a quantum algorithm. The calculation ends with a measurement, collapsing the system of qubits into one of the pure states, where each qubit is purely 0 or 1. The outcome can therefore be at most classical bits of information. Quantum algorithms are often non-deterministic, in that they provide the correct solution only with a certain known probability. An example of an implementation of qubits for a quantum computer could start with the use of particles with 2 spin states, down and up, typically written and, or and. But in fact any system possessing an observable quantity A, which is conserved under time evolution such that A has at least 2 discrete and sufficiently spaced consecutive eigenvalues, is a suitable candidate for implementing a qubit. This is true because any such system can be mapped onto an effective spin 1/2 system.
Bits versus qubits.
A quantum computer with a given number of qubits is fundamentally different from a classical computer composed of the same number of classical bits. For example, to represent the state of an n-qubit system on a classical computer would require the storage of 2 n-complex coefficients. Although this fact may seem to indicate that qubits can hold exponentially more information than their classical counterparts, care must be taken not to overlook the fact that the qubits are only in a probabilistic superposition of all of their states. This means that when the final state of the qubits is measured, they will only be found in one of the possible configurations they were in before measurement. Moreover, It is incorrect to think of the qubits as only being in one particular state before measurement, since the fact that they were in a superposition of states before the measurement was made directly affects the possible outcomes of the computation. For example, consider first a classical computer that operates on a 3-bit register. The state of the computer at any time is a probability distribution over the different 3-bit strings 000, 001, 010, 011, 100, 101, 110, 111. If it is a deterministic computer, then it is in exactly one of these states with probability 1. However, if it is a probabilistic computer, then there is a possibility of it being in any one of a number of different states. We can describe this probabilistic state by 8 non-negative numbers A, B, C, D, E, F, G, H, where A equals probability computer as in state 000, B equals probability computer as in state 001, etc. There is a restriction that these probabilities sum to 1. The state of a 3-qubit quantum computer is similarly described by an 8-dimensional vector, A, B, C, D, E, F, G, H, called a ket. Here, however, the coefficients can have complex values, and it is the sum of the squares of the coefficients' magnitudes that must equal 1. These square magnitudes represent the probability amplitudes of given states. However, because a complex number encodes not just a magnitude but also a direction in the complex plane, the phase difference between any two coefficients, states, represents a meaningful parameter. This is a fundamental difference between quantum computing and probabilistic classical computing. If you measure the 3 qubits, you will observe a 3-bit string. The probability of measuring a given string is the squared magnitude of that string's coefficient, that is, the probability of measuring 000 equals, the probability of measuring 001 equals, etc. Thus, measuring a quantum state described by complex coefficients, A, B, H, gives the classical probability distribution, and we say that the quantum state collapses to a classical state as a result of making the measurement. Note that an 8-dimensional vector can be specified in many different ways depending on what basis is chosen for the space. The basis of bit strings, for example, 000, 001, 111, is known as the computational basis. Other possible bases are unit length, orthogonal vectors, and the eigenvectors of the Pauli X operator. Ket notation is often used to make the choice of basis explicit. For example, the state, A, B, C, D, E, F, G, H, in the computational basis can be written as the computational basis for a single qubit, 2 dimensions, is and. Using the eigenvectors of the Pauli X operator, a single qubit is and.
Operation.
While a classical 3-bit state and a quantum 3-qubit state are both 8-dimensional vectors, they are manipulated quite differently for classical or quantum computation. For computing in either case, the system must be initialized, for example into the all-zero string corresponding to the vector 1, 0, 0, 0, 0, 0, 0, 0. In classical randomized computation, the system evolves according to the application of stochastic matrices, which preserve that the probabilities add up to 1, that is, preserve the L1 norm. In quantum computation, on the other hand, allowed operations are unitary matrices, which are effectively rotations, preserve that the sum of the squares add up to 1, the Euclidean or L2 norm. Exactly what unitaries can be applied depend on the physics of the quantum device. Consequently, since rotations can be undone by rotating backward, quantum computations are reversible. Technically, quantum operations can be probabilistic combinations of unitaries, so quantum computation really does generalize classical computation. See quantum circuit for a more precise formulation. Finally, upon termination of the algorithm, the result needs to be read off. In the case of a classical computer, we sample from the probability distribution on the 3-bit register to obtain one definite 3-bit string, say 000. Quantum mechanically, we measure the 3-qubit state, which is equivalent to collapsing the quantum state down to a classical distribution, with the coefficients in the classical state being the squared magnitudes of the coefficients for the quantum state, as described above, followed by sampling from that distribution. Note that this destroys the original quantum state. Many algorithms will only give the correct answer with a certain probability. However, by repeatedly initializing, running and measuring the quantum computer, the probability of getting the correct answer can be increased. For more details on the sequences of operations used for various quantum algorithms, see Universal Quantum Computer, Shor's algorithm, Grover's algorithm, Deutsch-Jozsa algorithm, amplitude amplification, quantum Fourier transform, quantum gate, quantum adiabatic algorithm and quantum error correction.
Potential.
Integer factorization is believed to be computationally infeasible with an ordinary computer for large integers if they are the product of few prime numbers, for example, products of two 300-digit primes. By comparison, a quantum computer could efficiently solve this problem using Shor's algorithm to find its factors. This ability would allow a quantum computer to decrypt many of the cryptographic systems in use today, in the sense that there would be a polynomial time, in the number of digits of the integer, algorithm for solving the problem. In particular, most of the popular public key ciphers are based on the difficulty of factoring integers or the discrete logarithm problem, which can both be solved by Shor's algorithm. In particular, the RSA, Diffie-Hellman, and elliptic curve Diffie-Hellman algorithms could be broken. These are used to protect secure web pages, encrypted email, and many other types of data. Breaking these would have significant ramifications for electronic privacy and security. However, other cryptographic algorithms do not appear to be broken by these algorithms. Some public key algorithms are based on problems other than the integer factorization and discrete logarithm problems to which Shor's algorithm applies, like the Make-Lease cryptosystem based on a problem encoding theory. Lattice-based cryptosystems are also not known to be broken by quantum computers, and finding a polynomial time algorithm for solving the dihedral hidden subgroup problem, which would break many lattice-based cryptosystems, is a well-studied open problem. It has been proven that applying Grover's algorithm to break a symmetric, secret key, algorithm by brute force requires time equal to roughly 2n/2 invocations of the underlying cryptographic algorithm, compared with roughly 2n in the classical case, meaning that symmetric key lengths are effectively halved. AES 256 would have the same security against an attack using Grover's algorithm that AES 128 has against classical brute force search, see key size. Quantum cryptography could potentially fulfill some of the functions of public key cryptography. Besides factorization and discrete logarithms, quantum algorithms offering a more than polynomial speedup over the best-known classical algorithm have been found for several problems, including the simulation of quantum physical processes from chemistry and solid-state physics, the approximation of Jones polynomials, and solving Pell's equation. No mathematical proof has been found that shows that an equally fast classical algorithm cannot be discovered, although this is considered unlikely. For some problems, quantum computers offer a polynomial speedup. The most well-known example of this is quantum database search, which can be solved by Grover's algorithm using quadratically fewer queries to the database than are required by classical algorithms. In this case, the advantage is provable. Several other examples of provable quantum speedups for query problems have subsequently been discovered, such as for finding collisions in 2-to-1 functions and evaluating NA and D trees. Consider a problem that has these four properties. The only way to solve it is to guess answers repeatedly and check them. The number of possible answers to check is the same as the number of inputs, every possible answer takes the same amount of time to check, and there are no clues about which answers might be better. Generating possibilities randomly is just as good as checking them in some special order. An example of this is a password cracker that attempts to guess the password for an encrypted file, assuming that the password has a maximum possible length. For problems with all four properties, the time for a quantum computer to solve this will be proportional to the square root of the number of inputs. it can be used to attack symmetric ciphers such as DDES and AES by attempting to guess the secret key. Grover's algorithm can also be used to obtain a quadratic speedup over a brute force search for a class of problems known as NP-complete. Since chemistry and nanotechnology rely on understanding quantum systems, and such systems are impossible to simulate in an efficient manner classically, many believe quantum simulation will be one of the most important applications of quantum computing. There are a number of technical challenges in building a large-scale quantum computer, and thus far quantum computers have yet to solve a problem faster than a classical computer. David DiVincenzo, of IBM, listed the following requirements for a practical quantum computer. Scalable physically to increase the number of qubits. Qubits can be initialized to arbitrary values. Quantum gates faster than coherence time. Universal gate set. Qubits can be read easily.
Quantum decoherence.
One of the greatest challenges is controlling or removing quantum coherence. This usually means isolating the system from its environment as interactions with the external world cause the system to decohere. However, other sources of decoherence also exist. Examples include the quantum gates, and the lattice vibrations and background nuclear spin of the physical system used to implement the qubits. Coherence is irreversible, as it is non-unitary, and is usually something that should be highly controlled, if not avoided. Coherence times for candidate systems, in particular the transverse relaxation time T2, for NMR and MRI technology, also called the dephasing time, typically range between nanoseconds and seconds at low temperature. These issues are more difficult for optical approaches as the timescales are orders of magnitude shorter, and an often cited approach to overcoming them is optical pulse shaping. Error rates are typically proportional to the ratio of operating time to coherence time, hence any operation must be completed much more quickly than the coherence time. If the error rate is small enough, it is thought to be possible to use quantum error correction, which corrects errors due to coherence, thereby allowing the total calculation time to be longer than the coherence time. An often cited figure for required error rate in each gate is 10.4. This implies that each gate must be able to perform its task in 1/10,000th of the coherence time of the system. Meeting this scalability condition is possible for a wide range of systems. However, the use of error correction brings with it the cost of a greatly increased number of required qubits. The number required to factor integers using Shor's algorithm is still polynomial, and thought to be between L and L2, where L is the number of bits in the number to be factored. Error correction algorithms would inflate this figure by an additional factor of L. For a 1000-bit number, this implies a need for about 104 qubits without error correction. With error correction, a figure would rise to about 107 qubits. Note that computation time is about L2 or about 107 steps in on 1 MHz, about 10 seconds. A very different approach to the stability coherence problem is to create a topological quantum computer with anyons, quasi-particles used as threads and relying on braid theory to form stable logic gates.
Developments.
There are a number of quantum computing models, distinguished by the basic elements in which the computation is decomposed. The four main models of practical importance are: quantum gate array, computation decomposed into sequence of few qubit quantum gates; one-way quantum computer, computation decomposed into sequence of 1 qubit measurements applied to a highly entangled initial state or cluster state; adiabatic quantum computer or computer based on quantum annealing, computation decomposed into a slow continuous transformation of an initial Hamiltonian into a final Hamiltonian, whose ground states contains the solution; topological quantum computer, computation decomposed into the braiding of anyons in a 2D lattice. The quantum Turing machine is theoretically important, but direct implementation of this model is not pursued. All four models of computation have been shown to be equivalent to each other in the sense that each can simulate the other with no more than polynomial overhead. For physically implementing a quantum computer, many different candidates are being pursued, among them, distinguished by the physical system used to realize the qubits. Superconductor-based quantum computers, including squid-based quantum computers, qubit implemented by the state of small superconducting circuits, Josephson junctions, trapped ion quantum computer, qubit implemented by the internal state of trapped ions, optical lattices, qubit implemented by internal states of neutral atoms trapped in an optical lattice, electrically defined or self-assembled quantum dots, for example the Loss DiVincenzo quantum computer, or qubit given by the spin states of an electron trapped in the quantum dot charge-based semiconductor quantum computer. Qubit is the position of an electron inside a double quantum dot, nuclear magnetic resonance on molecules in solution, liquid state NMR, qubit provided by nuclear spins within the dissolved molecule, solid state NMR Kane quantum computers, qubit realized by nuclear spin state of phosphorus donors and silicon, electrons on helium quantum computers, qubit is the electron spin, cavity quantum electrodynamics, CQED, qubit provided by the internal state of atoms trapped in and coupled to high-finesse cavities, molecular magnet, fullerene-based ESR quantum computer, qubit based on the electronic spin of atoms or molecules encased in fullerene structures, linear optical quantum computer, qubits realized by processing appropriate states of different modes of the electromagnetic field through linear optics elements such as mirrors, beam splitters and phase shifters, for example, diamond-based quantum computer, qubit realized by the electronic or nuclear spin of nitrogen vacancy centers in diamond, Bose-Einstein condensate-based quantum computer, transistor-based quantum computer, string quantum computers with entrainment of positive holes using an electrostatic trap, rare earth metal ion-doped inorganic crystal-based quantum computers, qubit realized by the internal electronic state of dopants in optical fibers. The large number of candidates demonstrates that the topic, in spite of rapid progress, is still in its infancy. But at the same time, there is also a vast amount of flexibility. In 2001, researchers were able to demonstrate Shor's algorithm to factor the number 15 using a 7-qubit NMR computer. In 2005, researchers at the University of Michigan built a semiconductor chip that functioned as an ion trap. Such devices, produced by standard lithography techniques, may point the way to scalable quantum computing tools. An improved version was made in 2006. In 2009, researchers at Yale University created the first rudimentary solid-state quantum processor. The 2-qubit superconducting chip was able to run elementary algorithms. Each of the 2 artificial atoms, or qubits, were made up of a billion aluminum atoms, but they acted like a single one that could occupy 2 different energy states. Another team, working at the University of Bristol, also created a silicon-based quantum computing chip, based on quantum optics. The team was able to run Shor's algorithm on the chip. Further developments were made in 2010. Springer publishes a journal, Quantum Information Processing, devoted to the subject. In April 2011, a team of scientists from Australia and Japan made a breakthrough in quantum teleportation. They successfully transferred a complex set of quantum data with full transmission integrity achieved. Also, the qubits being destroyed in one place but instantaneously resurrected in another, without affecting their superpositions. In 2011, D-Wave Systems announced the first commercial quantum annealer on the market by the name D-Wave 1. The company claims this system uses a 128-qubit processor chipset. On May 25, 2011, D-Wave announced that Lockheed Martin Corporation entered into an agreement to purchase a D-Wave 1 system. Lockheed Martin and the University of Southern California, USC, reached an agreement to house the D-Wave 1 adiabatic quantum computer at the newly formed USC Lockheed Martin Quantum Computing Center, part of USC's Information Sciences Institute campus in Marina del Rey. D-Wave's engineers use an empirical approach when designing their quantum chips, focusing on whether the chips are able to solve particular problems rather than designing based on a thorough understanding of the quantum principles involved. This approach was liked by investors more than by some academic critics, who said that D-Wave had not yet sufficiently demonstrated that they really had a quantum computer. Such criticism softened once D-Wave published a paper in Nature giving details, which critics said proved that the company's chips did have some of the quantum mechanical properties needed for quantum computing. During the same year, researchers working at the University of Bristol created an all-bulk optic system able to run an iterative version of Shor's algorithm. They successfully factored 21. In September 2011, researchers also proved that a quantum computer can be made with a von Neumann architecture, separation of RAM. In November 2011, researchers factorized 143 using 4 qubits. In February 2012, IBM scientists said that they had made several breakthroughs in quantum computing with superconducting integrated circuits that put them on the cusp of building systems that will take computing to a whole new level. In April 2012, a multinational team of researchers from the University of Southern California, Delft University of Technology, the Iowa State University of Science and Technology, and the University of California, Santa Barbara, constructed a 2-qubit quantum computer on a crystal of diamond doped with some manner of impurity, that can easily be scaled up in size and functionality at room temperature. 2 logical qubit directions of electron spin and nitrogen kernel spin were used. A system which formed an impulse of microwave radiation of certain duration, and the form was developed for maintenance of protection against coherence. By means of this computer, Grover's algorithm for 4 variants of search has generated the right answer from the first try in 95% of cases. In September 2012, Australian researchers at the University of New South Wales said the world's first quantum computer was just 5 to 10 years away, after announcing a global breakthrough enabling manufacture of its memory building blocks. A research team led by Australian engineers created the first working quantum bit based on a single atom and silicon, invoking the same technological platform that forms the building blocks of modern-day computers, laptops and phones. In October 2012, Nobel Prizes were presented to David J. Wineland and Serge Haroc for their basic work on understanding the quantum world, work which may eventually help make quantum computing possible. In November 2012, the first quantum teleportation from one macroscopic object to another was reported. In February 2013, a new technique, boson sampling, was reported by 2 groups using photons in an optical lattice that is not a universal quantum computer but which may be good enough for practical problems. Science, February 15, 2013. In May 2013, Google Incorporated announced that it was launching the Quantum Artificial Intelligence Lab, to be hosted by NASA's Ames Research Center. The lab will house a 512-qubit quantum computer from D-Wave Systems, and the USRA, Universities Space Research Association, will invite researchers from around the world to share time on it. The goal is to study how quantum computing might advance machine learning. In early 2014 it was reported, based on documents provided by former NSA contractor Edward Snowden, that the U.S. National Security Agency, NSA, is running a $79.7 million research program, titled Penetrating Hard Targets, with the aim of developing a quantum computer capable of breaking encryption vulnerable to quantum computers.
Relation to computational complexity theory.
The class of problems that can be efficiently solved by quantum computers is called BQP, for bounded error, quantum, polynomial time. Quantum computers only run probabilistic algorithms, so BQP on quantum computers is the counterpart of BPP, bounded error, probabilistic, polynomial time on classical computers. It is defined as the set of problems solvable with a polynomial time algorithm, whose probability of error is bounded away from 1/2. A quantum computer is said to solve a problem if, for every instance, its answer will be right with high probability. If that solution runs in polynomial time, then that problem is in BQP. BQP is contained in the complexity class P, or more precisely in the associated class of decision problems PP, which is a subclass of PSPACE. BQP is suspected to be disjoint from NP-complete and a strict superset of P, but that is not known. Both integer factorization and discrete log are in BQP. Both of these problems are NP problems suspected to be outside BPP, and hence outside P. Both are suspected to not be NP-complete. There is a common misconception that quantum computers can solve NP-complete problems in polynomial time. That is not known to be true, and is generally suspected to be false. The capacity of a quantum computer to accelerate classical algorithms has rigid limits, upper bounds of quantum computation's complexity. The overwhelming part of classical calculations cannot be accelerated on a quantum computer. A similar fact takes place for particular computational tasks, like the search problem, for which Grover's algorithm is optimal. Although quantum computers may be faster than classical computers, those described above can't solve any problems that classical computers can't solve, given enough time and memory. However, those amounts might be practically infeasible. A Turing machine can simulate these quantum computers, so such a quantum computer could never solve an undecidable problem like the halting problem. The existence of standard quantum computers does not disprove the Church-Turing thesis. It has been speculated that theories of quantum gravity, such as M-theory or loop quantum gravity, may allow even faster computers to be built. Currently, defining computation in such theories is an open problem due to the problem of time, that is, there currently exists no obvious way to describe what it means for an observer to submit input to a computer and later receive output.